I'm Tammy Schiller. I'm the director of the TechGrid. Just real quick, I want to let you guys know we're an innovation hub. The banners on the wall are the partners that are involved in this innovation hub, and we are here for you. We work a lot with our small and mid-tier businesses to minimize barriers, to help them do business with our government. We're also here to help our students from elementary school to college to help you with your STEM-related education. We just did Camp Hover. I have our champion of the universe here today. He's wearing his TechGrid t-shirt, and we had a lot of fun, and we'll be doing more of those events for you guys, and we hope to see you back here at the TechGrid. So without further ado, I'm going to introduce Dr. Pat Fettick. He is the resource behind the Distinguished Lecture Series. He finds these awesome people to come and speak to all of you. And I will have him come up here and he's going to introduce our speaker. Come on up, Pat.
Thank you everyone for coming. So we are later on you might want to mute your computer because it's coming back. This is fine. But yes, so we're delighted to have Professor Phil Baran giving us the lecture today. He's coming to us from Scripps Research. His title is Simplifying Synthesis with Radical Cross-Concord. So Professor Baran received his BS from NYU and a PhD from Scripps Research. He then went on to Harvard for his postdoc before going back to Scripps as a research faculty. So again, you all know how hard that is to go get your PhD from somewhere and then come back as a faculty. That's few and far between. Professor Baran's research finds new ways to circumvent the bottleneck of sustainable, scalable synthesis that allow organic molecules to more rapidly transform into viable therapies. So I could go and read the entire list of awards, but you totally miss his entire lecture. But Professor Baran has educated hundreds of scientists over the years, co-founded numerous companies based on research that was done in his lab. And like I said, I'd run out of time if I were to name all the different awards, but some of them, just a smattering: the Dansko Foundation Science Excellence Award, Emmanuel Merck Leadership Award, HCS E.J. Corey Award. That's who you postdoc for, right? EJ, yeah. And a MacArthur Fellowship. Professor Baran is also an elected member of the National Academy of Sciences, the American Academy of Arts and Sciences, and a fellow of the Royal Society of Chemistry. Without further ado, welcome Professor Baran.
Well, good morning, everyone. Thanks so much for this opportunity. Let me mute. There we go. This opportunity to be here this morning. I noticed some youngsters here today. That's great. I have 4 kids myself, and the oldest one is 17. Doesn't like science. I'll show a picture of her today. Organic chemistry is, I think, the most amazing form of science. And if you're someone who likes to play with Legos, or you're someone who likes to build things, organic chemistry is an opportunity to build on the molecular level. And it almost gives you the ability to play God, because you can make things which the world has never made before. Our lab over the past over 20 years has been interested in simplifying the practice of organic chemistry because it can be used for everything, from medicines, agrochemicals, materials, and even energetics. And when we started the laboratory, we became a little bit disillusioned to how people had been making molecules because it was very labor intensive, very long. And so we tried to shorten that, and we came up with this equation that makes it very easy for a young student to try to conceptualize how a synthesis should be done. Essentially, the only thing you should be doing when you're making a molecule is making skeletal bonds: carbon-oxygen, carbon-nitrogen, carbon-carbon bonds. The rest of what you do in organic chemistry is a waste of time. And so I'll try to systematically show you today how we tried to take this challenge and institutionalize a way of making things easier. And the way we like to do it is by embracing radicals. So radicals are sort of crazy reactive intermediates that historically have been viewed as too crazy, like a Tasmanian devil, in order to actually capture its reactive potential. And over the years we've been showing how that conception of radicals is maybe misplaced. And when we started the lab back in 2003, the overwhelming zeitgeist, or the feeling at the time, was that radicals could only be used in an intramolecular setting rather than an intermolecular setting, because taking 2 crazy radicals and putting them together seemed like too arduous of a task that would be impossible to achieve. And so today, over the next 55 minutes or so, I'd like to show you how radical retrosynthesis, or the employment of these crazy types of transient species, can actually be quite beneficial and simplify the practice of organic chemistry in an astoundingly simple way. Now, as I mentioned, when we started the laboratory, large molecules like this that are natural products, you try to make them, it's called total synthesis, have been made in ways that are very long and laborious, and it became very tedious for me to teach students to put molecules together because of all the steps involved. Imagine spending 5 years of your life and 40 to 50 steps to make complex molecules like that. And so we turned to a concept called ideality that I introduced before, which allowed you to shrink the number of steps in a dramatic fashion to make molecules. The nice thing about ideality from a student perspective is it places the student in the form of an inventor. So you're always making disconnections with a question mark over the top of the arrow, asking yourself, how can we bring this new transformation into being? And in doing so, it's rather agnostic as to structural type. So you can use this to make things like terpenes, or alkaloids, or peptides, or even more complex structures such as complex oligonucleotides. So I don't have time to talk about this today, but over the past few years, we've been working in the area of oligonucleotide chemistry to simplify how these molecules are made as well. Now, embracing ideality means that you become an inventor. And as a course of this, trying to make these complicated molecules over the years, we got interested in the area of radicals, as I'll talk about today, but we also got into the area of electrochemistry that I'll briefly touch on as well, as a way of harnessing the redox chemistry of molecules directly by simply electrocuting them. So ideality is a really useful equation, and if you're interested in how we've embraced this idea to make molecules simpler over the years, we published a review a few years ago that summarized around 14 of the various natural products we made in that 4-year period. So if you're a student who's interested in the area of organic chemistry, putting molecules together, that reference at the bottom gives you a taste of what the laboratory has been doing over the past couple of decades. It allows you to do things like this. This natural product had been isolated previously by taking kilograms of species, sponges from the bottom of the ocean to make a microgram quantities of this natural product called portamine. And by harnessing the power of organic chemistry, we were able to make gram quantities of this natural product that is now being licensed by large pharma companies for its utility in anti-cancer work. So let me get you into the world of radical chemistry. We started this area 20-something years ago by looking at this very simple natural product called hapalindole-Q that was isolated from the ocean. And the way people had made this before was really relegated to polar bond analysis. So an enolate alkylation like this, or a classic Diels-Alder reaction, lets you make a molecule like this in a number of steps, but it is tedious. And most of the steps that are used here are not making skeletal bonds at all. We decided to disconnect it kind of like a child. We just took the two pieces apart and achieved an oxidative radical coupling between carbone, which is found in spearmint, it's found in plants, and indole, which is a coal tar byproduct. Put them together without any protecting groups at all and made it on a decagram scale. That was our sort of intro to radical chemistry. But there are really two types when you think about radical cross-coupling. There's the innate and there's the program. The innate is basically taking advantage of a radical's natural inclination to react with everything. And then the program is a more strategic way of taking advantage of radicals that you generate a radical and you strategically couple it to some other moiety with precise control. And that was, at the time, rather cutting edge. And it allows you to make molecules in a very simple fashion. So for example, this medicine that Merck scientists were trying to make required 5 steps, and it only proceeded in 3% overall yield. And the reagents over these arrows are a listing of some of organic chemists' least favorite reagents, like diazomethane, which is super toxic, and TeBe reagent, which is like a fuming volcanic lava in a bottle. Alternatively, you could take 2 simple commercially available materials, this sulfonate-derived radical precursor, that pyridine bearing a B-pin, which is commercially available, dump and stir them together, and it allowed the practitioner to make the exact same molecule in a fraction of the amount of time by taking advantage of innate radical cross-coupling. So we introduced these species called zinc sulfonates about 15 years ago, and it allows you to controllably generate radicals that are of strategic value to medicinal chemistry. And to make a long story short, these reagents are now widely commercially available. They are found in hundreds of patents in the pharmaceutical sector. They're used all the time to take very valuable small alkyl substituents and to throw them onto medicinal candidates. We also went to the world of olefins. Olefins are perhaps the most widespread functional group on planet Earth, and we decided to come up with a way to generate a radical from an olefin. And in doing so, using simple iron salts that are found in Earth's crust, you could generate a radical and make new carbon-carbon bonds. This reaction was invented about 10 years ago in our laboratory, and since then has been used in over 60 total syntheses by labs around the world to make all of the blue bonds shown in these highly complicated natural product structures. This reaction is really, really valuable for making congested carbon-carbon bonds that would be very difficult to make in any other way. And here's an example of where it can be used. So for example, this compound had previously been made by making an anomeric chloride, followed by an anomeric stannane, followed by an anomeric lithium. These are all species that nobody wants to use. Alternatively, you can take a simple commercially available glycal and acrylate, which is a byproduct from the polymer industry, dump and stir them together, and the reaction gives you this exact same product with minimal labor. In fact, this reaction is so simple, it can even be done in beer or wine or tea. We then went on and asked the question, could you take molecules that have substituents that are already present in a molecule and turn them into more valuable substituents, such as this boron residue? Boron is found in a lot of medicine. However, every time a boron residue is found, the practitioner needs to do a retrosynthetic analysis or a design plan that is based on a single boron atom. It's a completely backwards way of making a molecule, and it requires a lot of labor. Alternatively, you could start with a native peptide that has a carboxylic acid and have it transmutated by doing a decarboxylative borylation, shaving the time to make molecules like this that are found in many medicines by an order of magnitude. For example, this complicated antibiotic, often known as the antibiotic of last resort, vancomycin, could be converted into vancomycin within a day of work instead of 5 years of work. Now, we made this molecule very quickly and found that it's not a great antibiotic, but imagine being a graduate student spending 5 years of a PhD only to find out that you didn't make a very potent antibiotic. We could find out the answer in a single day. You can use this chemistry also to install olefins. So you can decarboxylate and install an olefin, and you can compare that to the state of the art. Normally, this sequence here is shown in a 7-step sequence using a miserable set of witch's brew of reagents to get a compound, which alternatively can be made in simple 2-step sequence by using the commercially available acid and directly coupling. You'll note that radical chemistry often doesn't need protecting groups, and the reason for that is because radicals operate in an alien landscape that don't talk to the normal 2-electron chemistry that organic chemists have been associated with over the past 70 or 80 years. You can even use this to install alkynes. So this unnatural amino acid is widely used in biological studies. However, the way you make it uses a lot of pyrophoric materials, meaning it can set your lab on fire. Alternatively, you can start with the glutamic acid, which you can buy at Trader Joe's, and couple it with acetylene gas, which is nearly free, and you get the exact same product by doing a decarboxylative alkynylation. Some of the key people behind this are shown here, and they're all off in their independent career. Chao is a professor over in China, Pep is a professor at Max Planck in Germany, and Jacob is a medicinal chemist at Bristol Myers Squibb. Radical retrosynthesis has exploded into the organic chemistry sphere. It's now widespread. Some of the reactions we've developed are shown in this box shown here. And there's a lot of really interesting applications that unfortunately I don't have the time to talk about. But for example, these complicated polypropanates shown in the bottom left normally need 2-electron logic, aldol, and you need to know a lot of chemistry to make them. And now this decarboxylative logic allows you to make these things kind of the same way you would put together Legos in your bedroom. You can use this logic to make complicated natural products. It's been done now hundreds of times in the field, and here are 2 recent examples, one of which I'll focus on in just a moment. There's been reviews written about this topic of how radical retrosynthesis can streamline the way you make things like terpenes, but also alkaloids and a number of other useful natural products. Now let me just show you that from a conceptual standpoint, doubly decarboxylative cross-coupling is very similar to the late great Bob Grubb's work on olefin cross-metathesis. And in that work, you may recollect that you can take two olefins and put them together to make a new olefin and liberate ethylene gas. And in a similar vein, doubly decarboxylative coupling allows you a similar strategic benefit. You take two different acids, you put them together, you lose CO2 gas, and you make a new carbon-carbon bond. Why focus on carboxylic acids? Well, because like olefins, they're found everywhere. You can buy thousands of them, and they're cheap. Let's take a step back for the students and think about how people make carbon skeletons in general. There's really only three ways of making carbon skeletons. And you might say, that some of you who know organic chemistry very well might say, well, that's an exaggeration, but it really isn't. I'm going to summarize in the next 3 slides about 150,000 publications. The first 50,000 publications is shown here. So people make carbon-carbon bonds or carbon-carbon skeletons by making unsaturated systems and then saturate them. You can use a Wittig reaction, a Suzuki, a Heck, whatever, and then you hydrogenate. For example, look at the steroid molecule that was made by these medicinal chemists. It was 7 steps long, and only 1 step of these 7 steps actually made a carbon-carbon bond. The rest of this was a complete waste of time. Now, the chemistry shown here is rather simple. So if you're an undergraduate doing this chemistry, it can be rather appealing because the columns are nice, the reactions look really good, the TLCs are pretty, but like a hamster running on a wheel, you're not really making much progress at all. Alternatively, you can take a commercial steroid, very cheap, couple it directly with that other acid, and in a single step, go make yourself a coffee, and when you come back, you get the exact same product in 2 hours instead of 1 week. The second way of making carbon-carbon skeletons and bonds is by directly making them. So things like alkylation of an enolate or a boron-alkyl Suzuki reaction, for example. So here is an example which is emblematic of the 50,000 papers in this area. This is from a medicinal chemistry group. They're trying to make medicine, and they try to make this unnatural amino acid. And it takes them 7 steps. Go ahead and look at the conditions on these arrows. For those of you who are organic chemists, you'll recognize that these are miserable reactions. Enolate chemistry, Grignard reactions, chiral auxiliaries, and at the end of the sequence, you finally get out the desired compound. Alternatively, if you'd like to do something else with your life, you can simply take glutamic acid, a simple keto acid, dump and stir them together, and within 2 hours, you get the exact same compound as a single enantiomer. Glutamic acid, of course, you can buy either enantiomer, and it's very, very cheap. The third way of making carbon skeletons is the most funny way, because here, people don't make any carbon-carbon bonds at all. Instead, what they do is they find, like a Christmas tree, they find a tree, and then they trim it, they decorate it, they put an ornament on it. So for example, this is another one from a company trying to make medicines. These folks wanted to make this unnatural amino acid, and in order to do it, they identified a carbon-based starting material, and then with a hammer and tongs, they decorated it, they used all sorts of toxic reagents, and they finally made the desired product. Again, if you're an organic chemist in the audience, take a look at the reagents on these arrows. Does anybody want to use this stuff? Nobody wants to do this chemistry, but they keep doing it. Alternatively, you take aspartic acid, which is really, really cheap. You can buy it at Costco. Couple it with a pipacolic acid, and within 2 hours, get the exact same product. So the question you may be wondering, maybe even the youngsters might be wondering, is why is this guy talking about this stuff? Why do people keep doing this? The year is 2026, and people keep doing this stuff. Why? And the answer comes from the basic way you were educated. So we have some kids here today. They probably remember when they were young, their parents taught them about opposites being attracted to each other. And magnets. You played with magnets when you were kids, right? And then when you get to college, they're going to teach you retrosynthetic analysis of organic compounds by taking advantage of that innate knowledge you have about polarity. They'll tell you to identify the delta plus or the partial plus and the partial minus, and then to disconnect between the plus and the minus. That's the way all adults were taught organic chemistry. And it is systematically led to things like the protecting group industrial complex and all of the sort of worrisome and wasteful steps of organic chemistry. There's a better way to do organic chemistry, and it relies on divorcing yourself from polar bond analysis. Now you may say, hey Phil, can ChatGPT or robots or something, computers, help you with this problem? So we went to the computers and we asked the computers, hey, can you give us an analysis of compound 1 and 2? And guess what the computer did? The computer spits back out the same trash that we learned for the last 80 years, because that's how it was programmed. But if I gave one of the children in this room a plastic molecular model of compound 1 and gave you a bucket of plastic building blocks, very likely the kids would say, oh, hey Phil, I found a square and I found a hexagon. Can I put those two together? And because you haven't learned the rules of organic chemistry yet, you would be right. Radical retrosynthesis divorces yourself from polar bond analysis and therefore gives you the most convergent and concrete, simple, direct disconnection straight away. You don't need 9 or 7 steps to make compounds like this. You only need 1. And that's because you don't know yet polar bond analysis. All you know is radical retrosynthesis. It makes your life a lot easier because now the world of Lego chemistry comes to organic chemistry. You know, when people ask me, hey Phil, what do you do? Or kids, I say, well, organic chemistry is kind of like putting together Legos. But those of you who do organic chemistry know it's a big lie. Because if Legos were like organic chemistry, that company would have gone out of business many years ago. The practice of organic chemistry is very difficult. It's not like Legos at all. Most of the things you want to do don't work. But now with radical retrosynthesis, that vision of putting together things like Legos can actually come to fruition. So in this paper, we've removed around 160 steps from the way molecules are made. Throughout this lecture, I'll show you, if you combine it all together, the deletion of about 750 steps from the way you need to make organic molecules. Here's an example of a compound called saxitoxin that was isolated from shellfish. It's a poison, but it's also a potential medicine for pain. And the way it had been made over the years, dating back from the year I was born in 1977, is very laborious and time-consuming, and can be used to make only a trace quantity that you can't even see of the final natural product. But Anna and Yinlang, shown here, were able to devise a route using radical retrosynthesis that allows Anna, the student on this project, to make decagram quantities of this compound in 1 week with her own 2 hands. And here it is, just taking advantage of 2 simple amino acids, serine and proline. We were able to relegate this synthesis to something that's really child's play at this moment. So here's a synthesis. You take a serine derivative, you take a proline derivative, submit it to a biocatalytic CH oxidation, couple these 2 fragments at the top, 30 and 32, to a radical cross-coupling, and that's it. That's the carbon skeleton of saxitoxin. Following that, you install the remaining guanidine residues, and then you submit it to an extraordinary oxidation sequence that forges a new NC bond, delivering decagram quantities of the final precursor to saxitoxin. We only take small quantities of this and convert it to the natural product because it is extremely toxic natural product. All right, so throughout the course of this work, we have been using for years electrochemistry, which is something that when we started in the lab was really a boutique area that no one in organic chemistry, certainly no one at Pfizer or Novartis would ever consider using electrochemistry, but we decided to work on it. And it turns out it actually is now quite a powerful technique in modern pharmaceutical chemistry. And what we realized is that you really need 3 things to get people interested in electrochemistry in the modern era. First, you need to educate them that electrochemistry is not a black art, it's not some weird science, it's actually really easy to understand. It's not an alien art. It is ET though, it's just not that ET. It's electron transfer. So if you understand how arrows move and electrons move in organic chemistry, it's very easy to conceptualize reactivity in electrochemistry. The second thing you need is a piece of equipment, because every time people were doing electrochemistry, it was like getting a degree in arts and crafts. They had to buy their potentiostat from somewhere, their electrodes from somewhere else, the computer from somewhere, and their entire fume hood was taken up with a bunch of alligator clips and wires. So we teamed up with a company called ICA that makes chemical equipment, and decided to invent a device that was as pretty as an iPhone and as functional as all that complex machinery. Those devices, now called electrosyn, are found all throughout the industry. There's thousands of them that are out there, and they're in every major pharmaceutical company. It has led to a renaissance and an explosion of interest in the area of electrochemistry. This is the only patent that I have that's an engineering patent. It's not chemistry. And if you're interested in the origin story of this device, you can look on our website for an hour-long lecture of how this device was actually developed. The third thing you need to focus on for electrochemistry is enablement. So you need to be able to show people, hey, here's something you can do that previously needed 10 steps, and now you can do it in just one. So electrochemistry is more than just sustainability. It's also just getting you to the product that you want in a fraction of the amount of time that was required before. And if you're interested in this area, we wrote a review on it. You can take a look at that paper. It'll get you up to speed, everything you know to do electrochemistry in a laboratory within about 10 or 15 minutes just by looking at the figures of the paper. All right, and if you're interested in how this differs or contrasts with photochemistry, photochemistry and electrochemistry are very similar in that they're both aiming for redox. So balancing redox states is important for almost every bond formation you want to make in organic chemistry. But let's take a step back and ask the question, what do people in modern pharma chemistry, or anywhere they do organic chemistry, what do they do all day? And the answer may surprise you. The reactions that they do are boring. They're boring reactions because they work. The most useful reactions in organic chemistry turn out to be the ones that are the most boring reactions of all time. And if you look at these reviews from 10 years ago, you'll note that there's no radical chemistry in there at all. And we have asked this question for many years, why is it that radical chemistry hasn't taken off in the same way that all of these boring types of reactions have? And the answer really comes from my colleague, Barry Sharpless, who actually won 2 Nobel Prizes. And he defined what a useful reaction is. A useful reaction needs to have 3 things. Number 1, the starting materials need to be ubiquitous. You need to be able to buy the starting materials or make them anywhere. Secondly, the reactions have to have wide scope, which means that they have to have high chemoselectivity and tolerate many different functional groups that are on the periphery of an organic molecule. The third and most important part of a useful reaction, it has to be done by even a primate, that it has any primate with an opposable thumb. So if you can train a monkey at the zoo to do your reaction, that's probably going to be a reaction that becomes super useful in the future. Radical chemistry has 2 of those 3 things. The starting materials are super easy to get. The scope of the reactions are very high because radicals, as I mentioned before, don't care about your 2 electron problems. The problem with radical cross-coupling, all the chemistry I showed you for the past 20 minutes, is the redox. That's the problem. The redox requires things like a photochemical setup or an electrochemical setup or a large amount of a metal salt to get the redox in the right state. So the question we ask, and the question every engineer that's good really should ask, is how do you delete the most difficult part? Not keep adding complexity. Radical cross-coupling over the years, dating back to the 1960s, always required one thing, redox. Redox is a bug, it's not a feature. It's a curse, not a blessing. And so I've told you about many redox reactions that require electrochemistry, but what I'm now going to tell you in the last 45 minutes of this talk is how do you avoid all of the redox altogether? That's the key. If you can do that, you will relegate radical chemistry from being an academic curiosity to being something that everybody wants to use. And the clue came from an old reaction that when you take organic chemistry one day, you'll learn. It's called the Wolff-Kishner reaction. A useful reaction for deoxygenating ketones and aldehydes that goes via a diazine intermediate. That diazine intermediate decomposes via a radical to give you the product. And we wondered, could we take diazines and use those? The problem is, you can't buy a diazine. Those are the kinds of things that Pat uses in his missiles here to blow things up. They're too energetic. You can't have them in a bottle. But we wondered from this old paper at the bottom here that they had taken a hydrazone intermediate, reduced it, and then in situ at the end of the reaction, they saw this 5-exotrig cyclization product, meaning that there was a radical precursor in there, and that was our eureka moment, realizing that we now had potentially the most ideal radical precursor that ever existed. We call them sulfonyl hydroxides. Sulfonyl hydroxides are a new functional group that are crystalline, stable, easy to access from alcohols, ketones, even amines, and they represent the best radical precursor you could imagine because they do not require any redox at all. They are driven like a rocket to completion by loss of nitrogen gas, which is the greatest driving force in all of organic chemistry. And so here are some of the reactions that you can do. First, here's the team. led by Jiawei, Aaron, Jian, Jet, Haozhang, Kawa. And the bottom row of folks are all from Bristol Myers Squibb. So this was a collaboration directly with one of the largest pharma companies on the planet to try to see how we could take radical cross-coupling in the redox neutral mode to the mainstream. So the first thing we did is a simple innate radical cross-coupling, a Giese reaction. You generate a radical and it's captured, which is kind of boring. But here are some more interesting reactions, where you can take a sulfonyl hydrazide, react it with either a redox active ester or an alkyl halide to make new carbon-carbon sp3 linkages, which are some of the hardest bonds to make in organic chemistry. Look at the conditions over the arrow. It's just nickel, which is one of the cheapest metals on the planet, a ligand, which is actually derived from a pesticide, a small amount of base, and heat. That's it. Anybody can do this reaction, and I'll show you in just a moment. You can use this chemistry to make carbon-carbon bonds that are unsaturated as well. So carbons connected to aryls, alkynyls, and even alkenyl residues are possible. You can also make these valuable trifluoromethylated compounds that are useful in the agrochemical space and pharma sector. And finally, if you don't want to isolate the sulfonyl hydrazide, you can derive it in situ from the corresponding hydrazone by simply adding a silane to the reaction mixture. So these reactions shown in this slide were all done by our colleagues at Bristol Myers Squibb. They made libraries of these compounds, and for the organic chemists in the audience, what's interesting is the high level of chemoselectivity. So you can have very complex structures that normally don't play well with metal salts, and they have no problem at all working in this reaction. Now here's a simple compound. This hydroxyethylated pyridine, it looks very simple, right? It's tiny, but there's no good ways of making it. As of last year, the best ways of making it in one step are shown below, and they're all really bad. Now, you can take a commercially available hydrazine, simply add tazol chloride, nickel ligand base, and heat, and you get the exact product you want in what is conceivably the most cost-effective way of making a compound like this that currently is known. Here are some real-world examples from people at BMS that are actually trying to make medicine. On the bottom left-hand side is a reaction that didn't work with any redox technique because it wasn't scalable. You needed crazy engineering apparatuses, flow devices with pipes going everywhere, too complicated to do on scale, and now just dump and stir. On the right-hand side, the same thing. They couldn't scale up the redox chemistry, so the only thing they could do is a very laborious 6-step sequence. And now it's just dump and stir. Here's another example where decarboxylative coupling did not work for these people, but they used the hydrazine chemistry and it worked perfect. And here's another example of another team trying to make medicine, this one for anti-cancer activity. They tried every type of cross-coupling they could try, nothing was working, but the sulfonyl hydrazide chemistry worked out beautifully for them. You can also do late-stage functionalization. So for example, this medicine, kind of complicated, has a lot of different functional groups. If you're a medicinal chemist and you only want to functionalize that primary alcohol, how do you do it? There's not a lot of ways. Now you can simply do a Mitsunobu reaction, take the crude material, cross-couple, and get the exact product you want. You can scale these reactions up to a gram scale. I've run these reactions with my own 2 hands, even though my technique is not what it was when I was young. And the hardest part of running this reaction myself was just weighing out the starting material. It's simply dump and stir chemistry. You could do it on the podium right here in front of everyone. My daughter turned 16 a couple of years ago, and that meant because of California law, I was able to bring her into the lab finally. Now she has no interest in becoming a scientist or a chemist, but we forced her to do this reaction, and here it is, and she did the reaction, and at the end of it she said it was easier than baking cookies. So you don't need to be a chemist anymore to make carbon-carbon bonds. This is very easy to do with your own hands. Mechanistically, what's going on here? And this is arguably more important for the organic chemist in the audience. I might lose some of the back row here. It is definitely a radical, and we know that because the cyclopropane, which is spring-loaded, opens up. For the organic chemists, also focus on that next line, which is that competition between a 5-exotrig cyclization and a direct coupling. And note that the major product is A. I will return to that in just a moment. Now, why do we not need any redox? We're not adding any zinc, we're not adding any magnesium, we're not shining light on it, we're not electrocuting it. Where's the redox coming from? It's coming from the decomposition of the hydrazide. So as you lose nitrogen, you also propel nickel into the correct oxidation state, which is nickel 1, And that lets you sidestep all the redox. So the redox is built into the functional group, and the reaction is driven by the loss of nitrogen gas. Here is a computed transition state. We use computers to tell us how the reaction is working in real time at a molecular level. And this is the key person that did all that computation, a very talented postdoc from Caltech, David Gagan. Anyway, here is the mechanistic cycle. It's very simple. It's only one cycle. It uses a nickel 1,3 oxidation cycle. It goes through a standard oxidative addition, reductive elimination pathway. So very, very basic organometallic chemistry, not complicated at all. Easy to understand, and as you'll see later, easy to optimize and fine-tune. Now we went to the next topic, which is a question I have gotten for the past 15 years. At the end of every lecture, there would always be a student who asked the question, hey Phil, can you do these with control of asymmetry? Enantioselectively, meaning make only the left-handed one and not the right-handed one, or vice versa. And every time I had to roll my eyes and say, that's going to be impossible, just based on first principles, because it's known that once you generate a radical that, let's say, is left-handed, the minute you generate it, it becomes left and right, because it forgets everything. They have amnesia. If you saw that movie, Finding Nemo, they're like Dory. You make a radical and it just forgets everything about it. So you can't do a stereospecific radical cross-coupling because radicals can't remember anything. It's in the textbooks. Here's a textbook that says if you're going to do a radical cross-coupling and you're going to try to do it with an enantiocontrol, forget about it. It's never going to work because a radical forgets what it is at a picosecond time scale, which is so fast, it's like the rate at which a bond vibrates. It's so much faster than the blinking of an eye. This has been borne out experimentally. Over the years, people have shown if you have an enantiopure radical precursor, you generate a radical from it, it forgets all of its knowledge of what it was. And so this looked like something that would never work at all. But we thought, let's take a look at how the community has addressed this problem. And they've made a false analogy to one of the most useful asymmetric reactions in organic chemistry, the asymmetric reduction of olefin, hydrogenation. And if you have an olefin and you want to reduce it, you only need maybe 100 ligands, chiral ligands, and you can find one that's going to give you the proper enantiocontrol. And they thought, well, what if we take a radical, it forgets everything about itself, it forms an achiral intermediate, and then we capture that with a chiral ligand. That's an enantioconvergent cross-coupling. The problem with it from a first principle standpoint is that there are only around 5 kinds of olefins, so it stands to reason you don't need many ligands to figure out how to reduce them. But how many types of sp3 radicals are there? More than there are stars in the universe. So the idea that you're going to generate a chiral ligand that's going to control the fate of a radical coupling, it's never going to be general. So that approach is one that we immediately discarded in favor of one that is far more obvious. It's a form of modern alchemy. What if you took simple, cheap chiral alcohols and amines and leveraged them, converted them into high-value carbon-carbon bonds with high levels of stereocontrol? If you could do this, it would be a bit of a holy grail, because it would be like alchemy. You're taking something that's like lead or dirt, and you're converting it into gold. That's what we set out to do. And we use sulfonyl hydroxides to do that. Number one, sulfonyl hydroxides don't require redox, so the catalytic cycle is very simple. Number two, they go through a diazine intermediate, which means that that nitrogen, before it leaves, maybe it can grab a hold of the nickel, and the radical never forgets what it is, and then it just collapses and loses nitrogen. And finally, you can make these super easy from alcohols and amines. That was the idea. As it turns out, this works. We published this last year. You can take simple crystalline hydroxides, couple them with an aryl halide, and get high levels of enantiocontrol. We started this chemistry and got the first hit in, I think, November of 2024, and we were doing cartwheels in the lab because it was the very first time we saw a radical remember what it was. All we needed to do was change the ligand, change the solvent, and now we had high levels of control, meaning that we could capture that crazy radical and make it remember what it was. We took 2 different chemotypes that are found widely in industry, these 3 aryl pyrrolidines and pyperidines, that are found in about 80,000 medicinally important substances. And we showed how you could take these hydroxides and convert them to these chiral building blocks with high levels of control for the first time. The scope of this reaction is good. It works on THFs and THPs. But currently, acyclic systems don't work as well, and we're currently working on second generation conditions to fix for these more wildly reacting radicals. Anyway, you can use this chemistry to simplify your life. So for example, the compound in the white box was previously made through a very laborious sequence involving a Suzuki coupling, removing protected groups, putting them back on, separating through chromatography, misery and pain. Alternatively, a crystalline hydrazide and a simple iodoarine, dump and stir them together and you get the exact same product in a fraction of the amount of time. Similarly, for this pyrrolidine, required an enormous number of steps without any stereo control at all, could be done in one step just by dumping and stirring the two components together with high control. You could scale these reactions up. They're nice white powders, crystalline, stable, and they're not energetic, so they don't blow up. They're very safe, and they can be scaled up to give you enantiopure materials in very high yield. You can also solve the problem of diaster selectivity. Normally when you have a 1,2 cis-oriented species and you generate a radical, it always goes to trans because it decides to avoid steric hindrance. This has been a long-standing problem in the field for 80 years. Now you take a trans hydrazide, of course you get the trans product. If you take a cis iodide and you try to couple that under electrochemical or photochemical conditions, the major product you get is trans because the radical decides to be away from the sterically hindered substituent. Now, when you take a cis hydrazide, the major product you get is a cis product, which would be very difficult to get in any other way. And this holds true with a number of different relationships, 1,2, 1,3. What you put in is what you get out because the radicals no longer forget who they are. Mechanistically, this reaction is a little bit different than the one I showed you before. Before, it was an outer sphere pathway where the radical is generated like the Tasmanian devil, it just goes around the reaction and couples to the product. Now, it's an inner sphere pathway that is tethered together by the diazine, by the nature of the ligand on the nickel, and the viscosity of the solvent. That's been confirmed by DFT calculations, but also more importantly, through experimental means. So remember before I showed you this competition experiment of cyclization versus coupling. In the non-stereoretentive conditions, the major product was A. And now in the stereoretentive conditions, the major product is B. That means that the radical couples even before a 5-exotrig cyclization, which is one of the most fast radical-based cyclizations on the planet. And it doesn't matter how much nickel you have, 1 mole percent, 2, 5, 10, the ratio is the same. A back-of-the-envelope calculation will tell you that the stereoretentive protocol is therefore 100 times faster than the non-stereoretentive protocol. So you can use this in modern medicinal chemistry. What I'm going to show you now is how this chemistry has found widespread use in every company you can imagine, ranging from Gilead, Pfizer, Novartis, Merck, Bristol-Myers Squibb. Everybody is using this chemistry because they all want to install small molecular weight fragments to modify their late-stage aryl units. They want to fine-tune enzyme efficiency, solubility, metstat profile, and every time they want to put a small molecular weight group into the molecule, they need a completely different set of conditions. Now, the hydrazides offer you a unified set. If you want to install hydroxymethyl, aminomethyl, cyclopropyl, cyclobutyl, azetadinol, oxetanol, anything, use one set of reagents to get everything you want. If you go into organic chemistry in the future, for those of you in the back, you will have to memorize hundreds, if probably thousands of different reactions that form kind of like if you're a painter, those are the colors of your paint and the palette you use to work with. And every time you want to install a new fragment onto your molecule, underneath each of these square bricks is probably 50 papers you'll need to be aware of. And all of them carry with them their own degree of difficulty and structural constraints. Now with the hydrazides, you can use one set of reactions for everything. These are easy compounds to make. Any of you can make this today. They're crystalline, they're stable, and they're now also commercially available. And this table was put together. We collaborated with Biogen, Pfizer, Bristol-Myers Squibb, Enamine, a number of pharma companies. And as this slide is scrolling up, what's important to recognize is the great structural variety that this reaction series tolerates. One of the things that the medicinal chemists told me that resonated with me is they said, you know, Phil, what bothers us about you academic people is that you publish these papers where what we really want in the company are reactions that work in 10% yield on 90% of the substrates. And what you keep publishing are papers that work in 90% yield, but they only work on 10% of the substrates. So we said, okay, great. You give us the substrates for this table, and we'll do the reaction on the substrates you tell us, and that's what we did. So Pfizer, Biogen, all these pharma companies gave us their building blocks that never work, and we used that in the scope for this paper. We also field tested this chemistry to see how it compared with all the other methods that are out there. In these 6 case studies, you'll see that compared to everything else that's out there, these reactions work either in similar yield or better, but one thing it has advantage all across the board is that these are the easiest reactions to set up. You literally just dump things together and you heat. That's it. As I mentioned, these reagents are now commercially available from this small company, and they even sell a kit full of these reagents. Apparently they've sold dozens of these kits around the world to all sorts of pharma companies that are already using this to make medicine. Back to the mechanism. The mechanism of this reaction is unbelievably remarkable. It is unbelievable how tunable it is. So we studied this reaction using a technique called thermochemistry, which very rapidly tells you about the mechanism. It tells you what's important. And what it told us was that the only thing that's important is the rate of hydrazide decomposition to a radical. And the cool thing about this is it allows you to tune the nature of your radical so that you can generate the radical at any temperature you want. Sometimes you want to make your radical at hot temperature. Sometimes you want to make it cold. Simply by changing the substituents on your hydrazide, you can control the temperature at which your radical is liberated. So if you want a cold temperature reaction, you put electron withdrawing group. If you want a high temperature reaction, you put electron donating group. And here's how that can be used to improve reactions. So we tried this reaction under the initial conditions that I showed you before, only 15% yield. We simply used the principle of kinetic matching here, and we could improve the yield in threefold simply by changing the substituent on the hydrazide. All right, so you can use this to sweeten up chemistry as well. So these types of molecules, like the dapagliflozin, you may even know, maybe some of your parents use this molecule. It's called the sweet pea pill. It's for maybe people who have type 2 diabetes. This is $1 billion drug, and there are a number of drugs like this collectively selling about $30 billion a year. And the way people make this molecule is miserable. Polar bond chemistry, pyrophoric materials. The obvious way to make a molecule like this is just take glucose and your aryl group and dump and stir them together. That's the obvious way to make it. And people have been trying this for years without any success. But now the sulfonyl hydroxides allow you to do just that. So the students went to the store. You can buy dextrose powder at Walmart. They bought their solvent at Home Depot. And they mixed these things together, no protecting groups on your sugar, and in one step got the exact compound that was made before. Here are the students behind it. The same ones that made saxitoxin are responsible for this sweetened chemistry enabled by sulfonyl hydroxides. You can also use it to make carbon-sulfur bonds, which are widespread all over agrochemistry and pharma. And the normal way people make these, again, is labor-intensive because they use 2-electron polar bond chemistry. Instead, you can take a hydrazide and directly form a useful sulfonyl fluoride or sulfonamide just by dump and stir chemistry, going by the intermediacy of a sulfonate, which is a gateway to let you make all sorts of sulfur-6 derived compounds. So some of the examples from this paper, which are going to be published soon, there's about 70 examples are shown here. And again, it can simplify the way you make molecules. So look at how this compound was made before. 8 miserable steps to make this compound. Now, just take lysine, and in 2 steps you get the exact same compound as a single enantiomer. Starting from lysine, you can buy lysine at GNC. And it can be used even in really complicated scenarios. So we took erythromycin, which is an antibiotic which I'm sure many of you have used over the years, and you can directly convert it without any protecting group chemistry at all in a 2-step sequence to make this useful sulfonyl fluoride derivative of erythromycin. So over the years, radical cross-coupling has undergone an evolution. You're probably all familiar with this famous picture of SpaceX, how they simplified the development of rockets. And if you listen to the interviews of the engineers involved, they'll all tell you the same thing. The best engineers don't add parts, they delete them. And so what I want to get across to you is this point that redox neutral radical cross-coupling is the most refined way to go because it deletes all the complicated parts associated with redox. And in the final 10 minutes, I'll show you what is probably the most exciting chemistry we've ever done. And it's based on the well-known problem of making alkyl-alkyl bonds. These are the hardest bonds to make in organic chemistry. Here's an excerpt from a science paper where you can read it yourself. They mention it's the most important bond you can make in organic chemistry. It's still a frontier of organic chemistry. How do you take two organic molecules, put them together, get a new carbon-carbon bond, and control the asymmetry at that carbon atom? This is a holy grail problem that people have been working on since the genesis of organic chemistry. And today I'll show you one solution to this problem. And it really is the most difficult problem you can imagine in radical chemistry. Before I showed you taking a transient radical and coupling it to a flat aromatic structure. But what about taking two radicals and putting them together? Imagine coaxing two Tasmanian devils in a room to somehow get along in just the right way. It's a maddeningly difficult problem from a reactivity standpoint because those radicals like to do crazy things that are not what you want. And also, how do you control that enantioselectivity of that process? But if you could do it, it would be a game changer for the practice of organic chemistry. Take, for example, this compound that was used many years ago in a medicinal chemistry program. And the way they made it was, again, through a hammer and tongs approach, a miserable 7-step sequence. But if any of the kids in the back had plastic models, and we asked them, how would you make this molecule? They would just take the plastic model and go like that. The obvious disconnection is this one. But what it requires is that you harness the power of two crazy transient radicals. It seems to be an impossible feat. So we thought, well, the inspiration is what I showed you before. We were able to achieve a stereoretentive radical cross-coupling with an arrow residue, but how do we get a stereoretentive coupling to happen with two different radicals? And the idea was, if we got lucky and had a perfect synchronization of events, where in an alkyl iodide formed a radical, a hydrazide formed a radical, and the two somehow magically found their way together, maybe this would be a solution to the problem. And so we started with looking at this natural product called stenosine, which I think the kids might find entertaining. This natural product is actually excreted by the legs of this beetle. And this beetle subsequently can travel on water at around 70 centimeters per second, which is the equivalent of one of you running on water at 450 miles an hour. In addition, this natural product protects the little beetle, so as it's swimming on the top of the water at 70 centimeters per second, it's an antibacterial agent that's protecting it. So it's literally the chemical equivalent of wearing a Superman cape on its back. Now, this molecule has been made 4 times before, and they're all miserably long. I'm going to show you the shortest synthesis that's known. It's a long route. It uses polar bond chemistry, pyrophoric reagents, things that like to go boom, chiral auxiliaries. It's kind of miserable. And at the end of the sequence, they finally make the compound. Now, using stereoretentive radical cross-coupling, we can make this compound in 1 day. Simply take a crystalline, unprotected hydrazide, couple it with an alkyl iodide, and you see there, to the limits of detection, we just get around, it's 95% EE. On the HPLC, it looks like just one compound. I didn't believe this result when I first saw it, so I had to look at the data carefully myself, and it turned out to be general. So this is the amazing postdoc who worked on this natural product, Ian Lee, who's still in the lab. And then we went to this target compound shown here. Now this compound, as I mentioned before, is made for a miserable sequence starting with a simple purity-based aldehyde. If you look at the sequence, it's a very long sequence. Alternatively, if you could just take a crystalline hydrazide and couple it with an iodobromopropane, that would represent the shortest way of making this compound with lightning speed. And in fact, it works. It's hard to believe, but you can take this compound unprotected. I mean, I couldn't believe it. I still don't believe it, but it works. No protecting would require dump and stir at room temperature. It's not 45 degrees, it's just room temperature, and trifluoroethanol. And there's your product. Turns out to be general. It works with primary alkyl halides. It even works with secondary ones. I'll let you study this slide, but some of these compounds, I can't imagine how you would make them in any other way. And now you're relegating this to a very simple preparation of a crystalline hydrazide and a commercially available alkyl halide. So we think this is going to make a big impact in the field of organic chemistry, and we're looking forward to see where this goes. But mechanistically, it opens up an even more dramatic question of how in the world does it work? It shouldn't work, but it does. So we did radical clock experiments to try to, with a radar detector, to find out how fast are these things going. And we know in the case of the cyclopropyl iodide, that opens up super fast. But if we make a cyclopropyl hydrazide, it also opens up fast, but it gives a little bit of the ring-retained molecule, which if you do a back-of-the-envelope calculation, tells you that these reactions are taking place with near diffusion control, meaning they're as fast as an enzyme. They're like 10 to the 10th. They're faster than that beetle who's running on water. This is a team that's responsible for this work. Many of them are still in the lab, but most of them are off and they're starting their independent career very soon. You and Jawei are starting their independent career next month. David's still with us, Jed is with us, Jim, Yin, and the graduate student, Oliver. The mechanism of this is quite complicated. We've calculated it by high-level DFT calculations, and this slide exemplifies how we think that the chirality is maintained. The nickel interacts with that hydrazide, it forms a diazine, and it collapses to an alkyl nickel faster than that crazy radical can forget what it was. And that explains how we get the high level of control of coupling, and also how we get the high level of control of an antiospecificity. So with that, I will close and ask the question, has the era of radical cross-coupling arrived? Well, that remains to be seen. What I can say is that more and more people are using radical chemistry in industry. They're easy to generate from things you have. You have carboxylic acids, alcohols, amines, olefins. You can generate a radical from them using electrochemistry, photochemistry, chemical reducing agents. But in its most glorious manifestation, in my opinion, if you want to make a carbon-carbon bond for radical cross-coupling, it's redox neutral. Use a sulfonyl hydrazide, and you don't need any exogenous redox at all. So with that, I'll thank the folks that made this work possible. Leave it open for any questions people have. And again, thank Pat and the organizers for this incredible opportunity to visit you all day. It's a super honor, and I'm happy to answer any questions you may have. Thank you so much.
I have the mic if anyone has any questions for Dr. Baran.
Two independent questions.
Great.
One, have you been able to use the diacetyl peroxide as a source of the dialkyl product that releases CO2 with your system?
I think that might work. The problem is nobody in the industry wants to touch a peroxide. So while it could work, the problem is, once you see peroxide, first the process chemists, they check out. They're not going to be involved. And then the medicinal chemists all roll their eyes. So the key is we've got to make species that are readily accessible and ones that are going to be embraced by these people at these large pharma companies. And the peroxides are ones that they're going to just say, you're going to steer clear of. But in principle, I think it would work. If you generate the radical from the peroxide, it should be possible to intercept it the same way with nickel.
Accessible but not acceptable.
Exactly, yeah.
Okay. This is fascinating.
Thanks.
We used to have oompalong, now we got nopalong.
That's exactly right.
Some of my work in the 80s went nowhere because I didn't know about nickel.
Nickel is super useful for capturing radicals because of the persistent radical effect. So it's a great metal for capturing radicals, particularly ones that are transient.
Second question, have you been able to explore nitro decarboxylation or even installing a nitro group
from a
where your tassel
we have not tried to, that's a really good idea. And maybe Pat, if you want to follow up on that, we're willing to try that out because that could be really useful in the energetic sphere. To take a hydrazide and convert it to a nitro should be possible. We did, I think it was you who recommended we try decarboxyl nitration. We did do a few pilot studies using redox active esters, and it didn't work very well, but I suspect that's because we needed redox to initiate the decomposition of the redox active ester. In this case, because we don't need any redox, your dream of achieving radical-based nitration that you've been telling me for a while, I think we could finally achieve it with hydrazide. So that's a great idea. If you want us to look at that, we can do that. Yeah.
Thank you. Fascinating.
Got a few back there. Oh, there's one of the kids. Yeah.
Okay. Champion of the universe.
What's the school you teach at?
Scripps Research. It's in La Jolla, and we teach only graduate students, but we have interns from high school. We have interns from college. So when you turn 16, if you have any interest in organic chemistry, please email me.
So great talk, by the way.
Thanks.
I'm curious what you think, do you have any idea of the steric limit of the radical cross-coupling between alkyl radicals?
So
Like, can you do two tertiary radicals?
Oh, that's a great question. So we do secondary, primary, all works. The next frontier that we're working on next is how do you make quaternary centers using tertiary-based ones? And that, well, our work for many years in the area of decarboxylative coupling, we've published many papers on making quaternary centers using acids as the radical precursor. So I think with the right ligand choice, we should be able to get this to work with the hydroxides as well. But that's what the team is pivoting to now, because we just finished this work that I showed in the last few slides. But that's the next area is going to be just that.
Thank you.
Yep.
You've done a lot of great work, and you've also talked about divorcing yourself from certain organic chemical mindsets. Do you have a least favorite organic chemistry reaction, or a top 5 least favorite set?
I really am not a big fan of things like the Birch reduction. And we worked on the Birch reduction many years ago, back in 2017. Kleiser came to our office and said, hey Phil, we want to do a Birch reduction, which for the students, you don't know, it's like you're taking lithium metal or sodium metal, which explodes when you touch water, and dissolving it in liquid ammonia to reduce an organic compound. So it's like a reaction that nobody is really allowed to do in the modern era. And they asked us if we could invent a version that could be done in a kindergarten classroom. And so we did that using electrochemistry. So the Birch reduction is not a favorite one, but the new manifestation of it, we're big fans of now. In general, we don't like protecting group chemistry at all. We started the lab more than 20 years ago with advocating for deleting protecting groups from the repertoire. It's something that you often need to do. But in general, my top 20 least favorite reactions are all the reactions that you would put in the category of a concession step. What is a concession step? It's a redox manipulation, it's a functional group conversion, and it's a protecting group manipulation. Basically, for the students, when you make a molecule, you want to go from point A to point B. And a concession step is one that makes you detour. So imagine if you wanted to drive from here to La Jolla, and it took you 50 hours instead of 3. So to make it as direct as possible, you need to remove all of those concession steps from the practice of organic chemistry. Thanks, great question.
I have a question from the online viewers. Okay. So you mentioned that this process can be used for energetic materials. To your knowledge, is this process being used in the synthesis of energetic materials in the Department of Navy? If so, how safe is the process?
Okay, so I assume they're talking about hydroxides, because we worked on decarboxylative coupling with Jesse Sabatini, who I'm sure many of you know. We've published many papers with him. We've used decarboxylative chemistry to make energetic precursors that he's gone on in the process to make energetics. In the case of the hydroxides, to my knowledge, has not been used in the energetic space yet, but it's being used in scale-up chemistry at companies like Bristol Myers and Pfizer, and they have found that these compounds are very stable. So their energetic onset is over 100 degrees from the reaction temperature, which makes it safe to do on scale. So there's no issue using this chemistry, and the vendors that sell the reagents have also reported that they're indefinitely stable. So they're stable, they're fine, and they're not energetic.
Thank you.
Yep.
I wondered about the one example you gave about.
One more time, sorry.
I wondered about the example you gave of the product that was used for diabetes.
Oh, yeah.
Is that actually being made now in that manner, or is this very new?
It's very, we haven't even published it yet. It just showed you unpublished data. We're going to publish that paper probably next month, and we're going to patent it as well, because I think for the generics industry, making those in a much more cost-effective way, it's likely going to find some use there, because you can take glucose and derive a hydrazide from it in vinegar, and then take that crystalline compound and just dump and stir it together with your aryl halide, and make the compound in basically 2 steps instead of 9 or 10. So I suspect that it would be used in the future for the generics industry, because these compounds are already being sold to the general public, around 30 billion a year.
Right, and it would have to be, the patent covers the end product, it doesn't cover the method, right?
Correct. So when we publish the patent, we'll file a patent for just the process. Exactly.
If you guys need to get the students out, go ahead, but we'll continue to take questions.
I'm just curious about the nickel catalyst. I must have missed what it was. Is it like nickel bipyridine, or?
In the case of the aryls, it's just a substituted dipping.
Okay.
And in the case of the alkyl, you need a tridentate ligand.
Yeah.
It's a tridentate for the alkyl and bidentate, simple bidentate, just derived from BIPI pesticide.
Yeah.
Yep.
Is there any other type of chemistry you do?
Oh yeah, the thing is, when I go give these talks, they're sort of a snapshot of the chemistry that we do in the lab, but the lab has got about 35 people in it, tons of different interesting projects. My approach to chemistry is that when I have a student leave the lab, when they come back and visit in 5 years, I want the lab to be nearly unrecognizable. So we're always looking at the thing about chemistry. It's a lot like exploring the universe. If you want to be an astronaut one day, for example, the appeal to being an astronaut, I think, is that you're going to be like Star Trek and in exploring galaxies that no one's ever been to before. Organic chemistry is just like that. There's a world that no one has seen before, that nature has not even seen, that you can invent and discover. So yeah, we're doing all sorts of crazy stuff because the world of chemistry is so big and vast and exciting. And what we need are young students like you folks to find this to be interesting and go into this area, because if you get a degree in chemistry, you'll pretty much never be unemployed for the rest of your life.
What inspired you to do that?
I think it was kind of like I wanted to be an astronaut, but didn't have the dexterity and coordination to actually do that. And I love, art as well, but I'm not a good artist. So this is a great way of being an artist and an explorer at the same time. And once I found organic chemistry, I think I was like 15, it was like, became my oxygen. It was the only thing I could focus on, the only thing I had any interest on. When I was in college, I didn't even go on any dates when I was in college. I was just in the lab, and the only thing I knew was molecules. So that was it for me.
How many of the processes you've mentioned are actually used commonly in the industries?
Yeah, everything I've talked about today is used in modern pharmaceutical chemistry. The stuff at the beginning of the talk is much more widespread use just because it's older. Things like the sulfonate chemistry is, widespread. And the new stuff that I talked about at the end is being used at a number of pharma companies already. And the feedback has basically been that they love how it makes their life easier and to make things faster. So people and companies are not going to adopt chemistry just because maybe they like you. They're going to adopt it only because does it make their life easier and they can make things faster than they were making before. So everything in the talk I talked about is being used at companies like Pfizer, Gilead, Genentech, all the big pharma companies.
How much does it cost with and without radical cross-coupling?
That's a great question. So in many of these cases, like we talk about things, it's a great question. Like we talk about green chemistry, for example, being sustainable and good for the environment. But actually the best for the environment is just lowering the step count. So if it takes you 10 steps to make something and this radical cross-coupling will let you do it in 1 or 2, that saves money at every level. It saves money in terms of the labor cost, the time. Imagine if you're inventing $1 billion drug and you can get to that drug 1 year faster. That's a tangible amount of money that the company has saved. So the speed to getting to the compound you want is an enormous cost savings in terms of time, chemicals used, expertise required. So it's across the board.
So this is an open-ended question,
Sure.
but what interrelationship do you have with ag chemistry?
I have consulted with places like DuPont and Syngenta. We've worked with Syngenta quite closely for years. Agrochemistry is one of the most difficult, it's kind of like energetics, it's one of the most difficult areas of organic chemistry science. Unlike pharmaceuticals, where let's say you make an anti-cancer medicine, you can charge the patient or the insurance company $50,000 a year for the treatment, for example. If you're going to invent an agrochemical that kills pests or does something to protect a crop, how much do you think the farmers want to pay for a bucket of that? Almost nothing. So agrochemistry is super difficult because they need to make everything from earth, air, water, and fire. So we work with them very closely, but it's the hardest kind of organic chemistry because of the constraints of cost. Everything has to be almost free. So it's a lot of fun, but it's like intellectually vexing.
How long do you have to go to college for?
My story is a little bit different because when I was in high school, I got my degree at the same time, so I just had to go a couple of years in college. My recommendation would be to go to college as, if you decide that you found science or whatever field you like to be interesting, go there as little bit as possible. As fast as you can escape college, the better, if you know what your specialty is going to be. Because, I don't know how controversial it is. Most of what they teach you is not useful, to be quite honest. So sorry, parents who are here, but it's the truth. So the faster you can escape from college, if you know what you want to do, the better. So for me, it was 2 years, but if you can do it even faster, that'd be great.
What do we have to do so we can be able to do like organic engineering?
All you have to do if you find that if you like organic chemistry, how old are you?
12.
12. Okay, so in 4 years, you'll be legal age in California to intern in a lab and find a lab anywhere in the area that will let you intern in organic chemistry. But if you want to start learning about it, the great thing about this era, and back when I was a kid, if I wanted to learn organic chemistry, the only place I could go is the library and get a book. Now, go to YouTube. I mean, my classes are online, everybody's classes are online, so Intro to Organic Chemistry 101, there's some great lectures on YouTube, so by the time you're 16, you can already speak the vernacular of an organic chemist and you understand all the terminology. So that's what you can do now is watch YouTube videos, learn organic chemistry, and then when you're 16, get yourself into a lab as fast as possible.
Wait, one more, Mr. Baylor.
How many times in your experiments do you use the electrochemistry in that?
Oh, that's a great question. You know, we use electrochemistry a lot. The thing about electrochemistry is very addictive. So once a student starts doing electrochemistry, they really love it because it gives you a tactile feeling of the reaction. You can actually program your reaction like you would program on a phone. So it gives you a digital way to control your reaction. So we do it all the time. We have videos online you can take a look at of electrochemical reactions we do. They're a lot of fun. Thanks, folks. Thanks for coming.
Any other questions?
Oh, there's one more there.
So, I just wondered if you're connected to UC San Diego.
Oh, sorry, if what?
Are you connected to
Oh, yeah,
UC
we're not
San
connected,
Diego?
but I have students from UCSD all the time in my lab. It's very easy. If you're UCSD, very easy to do an internship at Scripps. Yeah. Yep.
Are you in need of a reliable source of tertiary alkyl radicals that form between 0 and 20 C?
And they're stable precursors?
They're manageable. They can be made from tridohydrazone anion with alkylation. There's a series of papers in the 80s from Baldwin and Bottaro. This work went nowhere, but it was intriguing.
That is a great.
All we did to the radical was reduce it with thiol and say we made oomph along on the ketone.
So you take the tridohydrazone, you deprotonate, you alkylate, and then that's your.
And
Oh, that's brilliant.
Tridoazo compound
Oh, that's
fall
awesome.
apart at 0.
Wow.
I
Okay.
thought it might interface with your work.
No, it's brilliant. I'm gonna look up those papers.
I went nowhere with it, but if you can use it, I would be thrilled beyond belief.
Okay, that's fantastic. If you have them handy and you can email them to me.
I don't, but they're in JR Chem and
Okay.
JCS ChemCom.
Okay.
They were widely distributed journals.
Great, that's good timing, because that's the other question over there. We're going to be starting to work on quaternary centers.
It was
and
out of
nutrition.
Baldwin's group.
It's out of Baldwin's group.
And when he was at Oxy.
Okay, great.
Anyone else? Back over to you, Pat.
So just as a thank you for coming and being our Distinguished Lecture Series speaker. So with gratitude for your contribution as a distinguished lecturer, thank you for your commitment to advancing innovation and the Navy TechConnect mission to connect ideas, technologies, and people in support of the warfighter.
Wow.
Thank you
very
so
much.
much.
Wow.